Cloud. Oi, gente. Sejam todos bem-vindos ao seminário nessa semana. Hoje nós temos a honra e o prazer de ter a doutora e professora Olena Linnyk. Ela é originariamente da Ucrânia, da Vinnytsia. Fiz a graduação na Universidade Taras Shevchenko de Kiev. Depois fiz doutorado na Universidade de Gießen com Ulrich Mosel e uma série de pós-docs em Frankfurt no grupo de Kassing e Helena Bratkowska sobre a mecânica e estatística fora de equilíbrio aplicada a colisões de íons pesados. Depois um pouco de tempo, ela virou professora visitante, adjunct professor em inglês em Frankfurt, e também, essa coisa aqui, infelizmente, não sei se pode existir no Brasil, mas na Alemanha é até bastante comum. Ela também trabalha para uma startup. Então, ela ainda trabalha na física de altas energias, no experimento NA61, que pesquisa a física de quark-gluon plasma, mas no mesmo tempo, ela trabalha em uma startup, sobre machine learning. Ela vai falar da conexão entre física e machine learning. Como sempre, se você quer assinar a lista de presença, põe seu nome no chat. Ela vai falar em inglês, depois pode fazer perguntas. Se tem perguntas urgentes, pode interromper, preferiria a discussão depois. Without further ado, Olena, please, you can start.
You put me on mute. And now I don't hear you, but that's very right. Very good that everybody's on mute. This is a phrase of the year 2020. You are on mute. So I didn't understand Portuguese. I'm sorry. This is why probably I will now explain again the same what you already did about who I am. And if anybody wants to ask a question and doesn't want that everybody hears the question, then the easy way, which I advise to my students, for example, is to write a chat message to me in private chat message. So you don't have to put questions in a public chat. If you put it in a private, then I will answer it and will not mention the names in case somebody is shy. It happens. At least it works very well with my students because then they are more free. That's to start. I heard the word startup out of what Georgia was saying, and I think I have nothing to do with startups, but okay, then I will move on. My understanding is that most people here study physics or do physics. That's why my topic will concentrate on the physics. But of course, I do a lot of other research too. And here, I hope you can see. So I am having 3 positions at the moment. As Georgia said, I'm lecturing at the University of Gießen, where I was the first to start teaching artificial intelligence, despite being a physicist. Right after I myself started doing it practically and understand that it's quite a useful thing. I was surprised to find out that in the 400 years old University of Gießen, there was no lecture in this direction offered by any department, including mathematics and computer science departments. So I just decided to help the situation. And now, not only there is a good interest in my lectures, but also the University of Gießen changed and started a new studying direction called data science. So one can get a bachelor or master in data science from University of Gießen. So my second job is in the Frankfurt Institute for Advanced Studies, and it's not in the order of importance, but just random order. Frankfurt Institute for Advanced Studies is very, very well known to Georgia, and Georgia is very well known in the Frankfurt Institute for Advanced Studies, short name FIAS. So FIAS was founded in the year 2006 by a group of professors from physics and neuroscience, with the idea to bring together scientists working on computational sciences, so including computational physics, and neuroscientists, with the long-term idea in mind to hope combine these brain efforts in order to either model the brain on a computer or solve scientific problems with the computer brains. So basically to combine AI and science, science and AI. So I'm very happy that quite many years later, at last, this initial idea led to the first results. And indeed, in the Frankfurt, in FIAS, there are now growing number of people who are applying AI for science or using scientific methods to improve AI. And I am representing now another spin-off that we are also trying to do something useful with these methods. And that I do as the head of the AI lab of the software company Milch und Zucker. For the German categories, this is still considered to be not a very big company, so it's a middle-sized company. It was until recently even small. Although it's 22 years old, as old as Google, and it is 140 people working in Milch und Zucker right now, out of which approximately 100 are programmers of different types. And our AI lab is not so large, but I think I'm allowed to say that we are growing, and we are at the moment approximately 2 PhD students and 1 postdoc and some master students. So we're doing a lot of collaboration with universities. Why do we do that? Because in the topic of artificial intelligence, you cannot just make a startup on one technology and then earn money for 10 years. It doesn't work, because in this field, everything changes so fast that, for example, 6 years is like last century. And one has to always invent something new and always go with the wave of science to follow it or to contribute. And only in this case, you have a hope to stay successful more than 2 years. Of course, there is also a possibility to make a startup and sell it after 5 years. Then you don't have to worry about it. But if you want to be successful long-term, then you practically stay in science forever. So some of the useful applications of artificial intelligence at the moment, so already today, although this field is developing and growing and it will be even better and better. So for example, until now, one famous application was that the CT scans of lungs could be analyzed with deep learning with better accuracy than a human, average human radiologist. So from a CT scan of lungs, a computer could tell if there is a cancer or emphysema or a healthy person with a better accuracy. Of course, the diagnosis in the best case scenario is not made based only on one picture, but the doctor takes into account all the other factors. But if we only look at the picture, actually the accuracy of the decision made by a human is not so high as we hope. And since Giorgio is recording, I will not tell the number, but you would be surprised how bad it is. Because I work with some radiologists in Gießen, I know. And of course, that was very useful recently when in Wuhan, the outbreak of COVID started. The very strong AI industry in China could react and provide the doctors in all hospitals in Wuhan with new technology trained to recognize COVID-19 in the scans. And that helped to stop the outbreak very fast. But of course, what is possible in China that within a few weeks, not only new software was developed, tested, trained, also deployed and introduced to hospitals. That is not possible in Europe, for example. Yeah. So, and one other application, which is a little bit less maybe life and death, is on in the center, these wavy lines. This is what has to do with physics, for example, not only the Higgs particle. Also, if you want to ask me, I will tell you what this Higgs particle has to do with machine learning. But if you look at the two plots in the middle, signal and noise, this is some snapshots from an experimental detector of the raw measurement of electronics. And for such clear case, even a student can recognize that the left plot is a signal and the one which is hidden behind a bit is a noise, obviously. Happens with electronics that it has noise, but not every readout looks so clear-cut. And very often, not even a very experienced physicist, I'm not saying radiologist, but a very experienced experimental physicist cannot tell from just looking. Moreover, all traditional methods about making cuts and estimations and fast analysis, well, methods which you can do online, which you can do before the data are reaching down, don't work. That's why the experiments are forced to write down a lot of garbage noise. And that is not anymore even possible after the upgrade of CERN detector, because the amount of data will be too large to write it down. And on the very right side, you see, for example, a chatbot. This is practically, if you talk to people on the street and not in the physics department of the university, what do they associate mostly with artificial intelligence? And they would say a talking robot, because this is what Turing test also is. And so existing already on very many websites, existing some chatbots. This is an attempt of some natural communication, which looks like a human talking to you. And I tell you that most of these chatbots are not really very smart. And we have spent in the company quite a lot of effort, time, and therefore money, and computing power in collaboration with one university in Germany in order to make a really smart robot which can talk in natural language and really understand and answer. And now I come to a very interesting point, which I wanted to tell you something here which you didn't know yet, and something which is very interesting. So what is understanding? Whenever I mentioned before to anybody, we are building or testing a chatbot in the company, they're like, but does it understand what it's saying, or it's just looking in a table? And therefore, I was very happy that a clever group in Budapest has made a lot of thought and defined a mathematical definition of understanding. That is a paper published very recently in 2020, which I really encourage all of you to read. And main author, Anton Jakovac, also can explain it so nicely that I will probably follow now his path in order, as I even stolen from him some transparencies, because nobody can explain better than him. So the idea is that, in a nutshell, classification is understanding. The robot who talks to you like a chatbot, or Alexa, or OK Google, they are, of course, just classifying. When I ask a question, then the chatbot is trying to classify to which category this question belongs. And depending on this category, or in the terms it is called intent, depending on this intent, you get the answer from the table. So it's only a classification. I classify the question, maybe I can also classify some information which is very important inside this question, like names, locations, and so on. But then based on that, I do a classification task. And AI is very good at classification tasks, but is it enough? And so the classification is understanding. I try to explain now here. So if I would ask a person, what do you see on this picture in the right corner? Some would answer, I see a lot of colored pixels. Another answer would be that I see a painting, which was, it's an oil painting, probably with some particular technique of paint brushing, so that the light falls in such wonderful way, and you can see also the golden ratio there. So one can talk about painting techniques. And another answer which a child would give, it's a woman with a cat. And another answer which a person who has idea about art would give me would be, it's a work by Renoir, woman with a cat. So which answer is the right answer? So my students always try to give the right answer. If you are at the test, then you have to decide what is the answer that the teacher is expecting. And that to show your understanding. So what did you understand from the picture? Tell me the right answer. In this case, all answers are legitimate and you cannot choose one right one. Because if you only have single apple, then you don't know what is intended to be understood from this apple. That it's a fruit, or it's an apple, or it's a red apple, or it's a particular sort, pink lady, for example. Only if I have a group of objects and I show you one object and the group, only then you can choose the right answer. In this case, that it's a red apple. So only in case of a context given, there can be understanding. There is no understanding without context. And in a context, to understand means to classify. I classify that this apple belongs to a group or not, depending on a feature. So basically, if I talk about understanding some word in a language, I can now give an example from the language. If I ask you, what means, no, good point. I'm not prepared here. What means an apple? Then I can say it's a fruit which is round, which is edible, which grows on a tree, and so on. Well, it can be cooked. So I give a lot of features about this object or this word in order to define the meaning behind it. So to understand something means to describe all the features of this object. And each feature is a matter of classification. So is it round or is it squared? Although I can classify the geometrical shape, I can classify the size, I can classify temperature, I can classify color, I can classify edibility and technique if it's from a tree or from the ground and so on. So classification defines understanding. And now we can come to the mathematical definition. We can now think about giving a number to each feature. It can be either a binary number, 0, 1, edible, not edible. It can be also a continuous number where I define the color by the RGB components, 3 numbers. So in principle, for most things in life, there is a large but finite number of features. And for this painting, for example, I can always describe it if I give each pixel a number for intensity and for the RGB components. So 4 numbers times number of pixels is the maximum amount of information which I can carry with this painting on the screen, with this picture on the screen. That's why the number of features in this CT scan or Renoir reproduction is always finite. So it can be described by a finite vector of numbers. And then it's easy. Then there is a very big connection to physics, because in physics we define everything through numbers, and the features described like velocity, temperature, and so on. And in each use case, in each question which we try to solve with, this case, physics, what physicists try is to reduce the number of important features and concentrate only on what's important, and to integrate everything else. So as physicists, we try to divide the world always into the important things for the understanding and not important rest, which is a renormalization group approach where we integrate the things out, or statistics, you can say, it's like thermodynamics and so on. So basically, there is a lot of parallels to the physics, and there is a little bit difference, because in the sub area of the artificial intelligence, which is called deep learning, the philosophy is the following, that we are not trying to reintegrate non-important features, because we build algorithm in such a way that it can analyze a very large number of features. And in this case, we can apply our algorithms to systems where there is a big number of important features. So we don't have to concentrate on such physics problems, for example, where we can describe the system with only 3 numbers or 4 numbers. It's not a problem. Somebody is not on mute. Please put this on. Thank you, Giorgio. So I'm saying that in the deep learning approach, for example, if we do image processing, then the situation is completely different to the traditional image processing, which was done until now. Because before, in video cameras, in CT scans, and so on, an image was first transformed into some features, like the distribution of intensities and other things. So after the data were pre-processed into features, only then they were analyzed with some statistical software. With the deep learning, we do not pre-process the data, but we push into the software every feature we can find, basically every pixel, its color, its intensity. For example, in these modern self-driving autos, and then the deep learning analyzes all features simultaneously without predefining in advance what is important. It is learning what's important already while learning everything else, so in the process of working. So when the car learns to drive, it decides by itself what's important. Sounds a bit scary, and this is why so many people are scared of the deep learning artificial intelligence. They say, we don't understand the understanding of this algorithm. But I want to show you in the rest of my time here on an example taken from physics, from the detectors, that it is possible to understand what the network made a decision based on. And okay, here I just talked about theoretical possibilities that AI can learn to understand and build a picture. But here is a practical example. This is AI had to make a description for a picture. And it describes the picture better than I would be able. For example, trees in a winter storm, maybe I would even say, but looking at the picture in the left down corner, I would probably not be able to say it so beautifully. The scenic route through mountain range includes 3 unbelievably colored mountains. It's almost poetic. And of course, the classical application on which every AI had to be tested first is classification of cats from dogs. And this is now, after you know that classification is understanding, you're now not surprised that the first test of the new technology was the classification task of cats and dogs, because there was this wonderful data set of cats and dogs prepared. Cats and dogs, by the way, if you know what is here, cat or a dog on a photo, write it please in the chat. I will tell you the answer later if you want. Basically, I didn't know what it is. For a human, sometimes it's not so easy to say. Because the cats can be of different sizes and different colors and different fluffiness, and the dogs also. So variability of each data set is very large. And even if we think of the representation in this vector space of features, the first of all would be really large vector space with a lot of directions. And secondly, the vectors for each photo, they will overlap. And so it's not so easy to differentiate. I will show you some very simple example now, so that maybe for the students among you. So let's think of only 2 features, because in 2 dimensions, a vector is just an arrow, and that everybody knows from school already, what the vector in 2 dimensions is. Or you can understand it as a point in 2 directions, like end of your arrow. So if you would look at 2 features of an insect, which is the length and the width, then you can differentiate caterpillars and caterpillars and ladybugs. Excuse my German. So caterpillars and ladybugs. Caterpillars are usually longer and ladybugs are so round. So if you would look at the features of a set of caterpillars and plot them with green crosses, and then the features of ladybugs in red, then you will see that they group in 2 clusters, and you can draw a decision boundary between the 2. And if you're good at finding the right decision boundary, then the rest is easy. When you see a new insect, you just look in which point the vector describing of this insect will end. And then you know that it's, for example, in this case, caterpillar. That's in a nutshell how it works, the classification. And die Grenze of German, that means the border. In case of only statistical error bars, in physics, for example, or what is usually assumed in medicine, the distribution around some hidden unknown central value is statistical, pure statistical, the Gaussian. In this case, there is a theorem which proves that the optimal border between 2 Gaussians is a linear border. So in this case, just take a linear function, fit it with a chi-square, and you get the optimal decision boundary between these 2 data sets, which overlap. That's why nobody's perfect. You will never be with 100% accuracy deciding which type it is, orange or the blue. But if you assume that you have only statistical error and no systematical error, then the decision boundary is linear. But our life is much more interesting than that. And indeed, this is, for example, the boundary which I find with machine learning, applying the k nearest neighbors method. It's a very simple method to understand. It's a very slow method to use. That's why nobody uses it in practice, but academically we are now looking. And the idea is that the probability of making the right decision if I use this boundary is much better, because probably the underlying distribution of these points was not just Gaussian statistical distribution. And then I can try to apply not just the KNN, but the modern deep learning algorithms, the neural nets. They give a smooth boundary, and also very high accuracy and work very fast. So what is the truth? In the world of a textbook, we know what was the underlying distribution of the points in this example. And only because we know in advance all the things, including distribution of systematical uncertainty, only that's why we can use the Bayesian method to build the boundary. And this is the ground truth in this case. It's not linear. That's all I want to say. It's not linear. Deep learning is also not perfect, but it's much better than a normal statistical approach. So it's beyond statistics. And the Bayesian, you can apply only to simulations. Because in simulations, you know exactly what causes the smearing, what distribution of the error is. In real experimental measurements, there is always much more than just statistical distribution, and you don't know how systematical uncertainty works. Citing a very clever man, Marek Gadzicki, the experimental device is not just shooting left and right by random. It is shooting in one direction more, and exactly in that direction which you don't like. And it always tries to confuse you. So if there is any device, it's as if it's working against you. So basically you will not see everything what is produced, you will see some things which were not produced, and you will not see them left and right symmetrically. So this is an interesting, complicated thing in physics. That's what makes it for me also exciting, that we go beyond statistical distribution. So what was so successful in finding the border between cats and dogs was the method of convolutional neural nets, not just simple neural nets from the 50 years ago, but in 2012, in the year 2012, was published a new idea which revolutionized everything, the convolutional neural nets. And the formula is for you, I don't know if it's enough. So basically, I don't have now, of course, all the time in the world to explain the details, but it's one of the technologies which made all the success in deep learning possible. It is working fast, it's finding nonlinear boundaries, it can distinguish cats from dogs, it can distinguish coagulant plasma in the crossover from the first order phase transition, for example, which colleagues in FIAS have proven in a paper. And now let's try to apply this very successful method to real data from an experimental detector, for example. So we can use normal traditional machine learning, which I said, for example, the KNN. There are also decision trees. Maybe one day you will hear the name. So decision trees are easy to understand because it's just a collection of if, then, if, then, if, then, if, then. So if it made a decision that this picture represents signal and not noise, then you can always just follow the tree to find out what feature made the algorithm decide so. And one tree is usually not working so well. So you have to make a collection of trees and then make a voting between them, like democratically. There is, and even then, they just don't reach such accuracy as the deep learning. And also, for example, in our attempts for the experiment, the accuracy was not, so yeah, if I mentioned maybe too much detail. So we find with the decision trees a lot of noise, but we also lose a lot of signal. While the neural nets manage better. And neural nets is also just an algorithm. It's not like I really have biological neurons somewhere. And these connections there, it just means that I combine linearly some inputs, like a sum of inputs, and give it to the next neuron. But between giving them, I make a nonlinear change of these inputs. and this is what makes it interesting, the nonlinear changes. This is called the activation function. It means in every small bubble on this picture, some non-linearity is introduced. And the connections, lines, are just linear transformations, like matrix multiplications. So we tried, for example, for some other data set in the company, something to do with texts, because we work a lot of text analysis in the company, found that convolutional neural networks were the best. And yeah, you don't have time to look at it, but the convolutional neural networks are not state of the art. They are from the year 2012. What I also wanted to say was this transparency, that the things which used for the images, for the cats and dogs, they can be also used for the texts. And they can also be used for the processing of signal and noise in the detector, or for the simulations of heavy ion collisions in theoretical group. So the same method can be used in many applications, and this is also what makes it so cool. And the state of the art in the image processing, what is in the best cameras at the moment, is much deeper than the convolutional neural networks used for the cats and dogs and normal deep learning. Because until the year 2018, it was an unsolved problem that after I connect these layers of neurons too many times, then my system cannot anymore optimize to the real minimum. It gets lost. So that's why it is limited how much nonlinearity I can introduce. So in order to get my border very nonlinear, I need many layers of neurons. But when I add many layers of neurons, which means I make my brain deeper, 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 our real brain has many, many layers. But when I make too many layers, then the information is lost while being transported through the layers. And that was the curse which didn't allow us to use the power of DABs. And that was overcome by another new theory in, so the problem was recognized in 2014 and overcome in 2018, if I remember right. In this, 2015, I lied, in this paper about ResNet. So this is the solution of this problem. And the problem has a name. The name is called vanishing gradients, but because I didn't give you a course of the deep neural networks and didn't explain where the gradients come, so I thought maybe it's not a very useful name for you, why it's called vanishing gradients. It's more important to understand what it means. And to understand what it means, it's just that information through the layers every time is a little bit lost. And when you make it too deep, it's lost completely. And so you cannot go deep enough in order to describe the most complicated systems. In 2015, the solution was introduced for the image processing, of course, at first, which solves this problem. It's called ResNets. And even people who have an idea about neural nets sometimes haven't yet understood what it is. And it's actually very simple. So the ResNet introduces these additional connections between layers, jumping over a few layers. In addition, so it's like a parallel highway. What it means, it's called residual connections because of the same thing that the students do with Giorgio in the statistics course, is that when you are trying to fit a very wiggly function with a smooth function, a few parameters, beautiful, just 1, 2, 3 layers needed for it, but it cannot describe the residual. So it would give a smooth approximation to the function, but there is some residual left, which is not described. And then you jump to the next block, which is now describing the residual. And again, the next block will be small and simple, where you don't lose any information and can fit the residual also with a smooth function. then still something is left. And so you iterate until you can describe in principle every fluctuation. And that is one of the problems that in applications of AI, when we think about now, this is a theory is very easy, but when you do it for a real problem, then you have to be careful that you don't overfit, for example, that you don't try to explain the fluctuations. And that is another, a topic of minimum 1 or 2 lectures another. How do you notice that you are an overfit? How do you work against it? But at least you have to have heard the name at least. One can do it also with texts, and we did, of course. And now, you know, we can also apply it for prediction of the activity on the website, for example, or reducing bias, improving performance. Now come to the physics. So if we have an experimental detector, for example, which has a TPC as one of the main parts, I, of course, work in the SHINE collaboration as adjunct member. So these red parts in the left picture are the so-called TPCs. The TPCs are the detectors which have a great advantage that they measure almost everything. But the disadvantage that because of that, they can also produce noise. That's very simplified. I know it's very simplified opinion about the TPC, but I think for this lecture it's enough. And it looks like a big gas chamber with a readout on one side full of electronics. And each pad, you can think of it as a pixel, only it's much bigger, of course. But in principle, as a student, you can think of a detector inside the camera in your mobile phone, and that has pixels, and this one has pads. Only that the pads in this type are a bit long. The carpenters, not ladybugs. And because they are long, the resolution in one direction is much better than the resolution in the other direction, but that's okay. It's built exactly this way because we need resolution in this direction. And basically the greenish, yellowish picture you can see in the right upper corner is one example of one cluster which was detected. You can see these black points are the electrons which are drifting to be read out by the electronics. So in the ideal world, each particle traveling through the detector produces a signal, such clusters firing on the pads. But not each cluster which we measure with the electronic is a real signal of a particle. Sometimes there are also noise clusters. And this green, blue, yellow points show one example of such a readout where we look at 11 pads, so the central pad of a cluster and 5 pads left and right from it. And we have, I think, 20 or 21 timestamps. Between timestamps, we know that it passed from one timestamp to the other, I think, a few, okay, I don't want to lie, microseconds, so a small fraction of a second. So we know, of course, that from left to right, time passed. So we measure from the electronics with such small delta t. And now what we asked deep learning convolutional network, for example, or other machine learning algorithms, we applied also decision trees and ResNet and so on. So we tried to devise an online filter which could, from all these on the left side, you see these great points as the clusters which were read from one event. And we want to decide which of these clusters were real signal and which were noise. So in the ideal world, we want to have only true positives and true negatives, no false positives, no false negatives. So that's impossible. Of course, there is also an error. But basically, we want to just be left with these orange points, which are the real traces of real particles, and to throw away all the green things. In this picture, they are green. This is a noise from the electronics. And so this division has to be done also so fast that we can make decisions before writing down the data. So it limits the available computational technologies very much. And so we have to work with machine learning and deep learning because all the other methods are too slow. All the other methods failed to do it, at least with such speed. And then we work with two groups in Poland and work on the alternative methods simultaneously. And we found that there are, let's say, 3 directions which are most useful. One direction is ResNet. As I just said, this is state of the art. This is the best what exists in the image processing. And we have 95,000 trainable parameters in the network. That's why the network is relatively slow. But on GPUs, it's fast enough because it can be parallelized very fast. And we have 92% accuracy in details. We can remove 90% of noise, where we unfortunately have to throw away 5.5% of signal. The collaboration says that these numbers are within already specifications. Now, validation. Did we overfit? If we fit on one part of the detector, it still works on the other, losing 2% of accuracy. That means we didn't overfit so much, but we still have to work on it. So now the interesting part, ResNet is a huge network. How can we even understand what the decision was based on? That's why my student had a cool idea. First, we said he's crazy. He has built a network of only 2 neurons. It's trivial, it's very simple. And of course, these 2 neurons each gets input from the whole matrix of numbers. The 2 neurons alone, after training, were 89% of the time correct. So almost as good as a complicated network. And it has only 400 trainable parameters. So with this simple network, we can throw away 87% of noise, and we have to throw away 8% of signal, so it's not as good as a state of the art and not within specifications of the collaboration, but that was not the point. We wanted to first, we just use it in order to see inside the neurons, because with 2 neurons, it's easy, you just have 400 parameters. So we plotted these 400 parameters. So he plotted these 442 parameters on such metrics. And basically when this value on the 3D plots points up, it means the probability, when there is a signal in this point, and the probability the signal is higher. So the weight points toward decision for the signal. And when the weight points down, the parameter points down, that means it's probably noise. From 3D plots, nobody can understand anything. That's why we rotate it. And then we can look from all directions and understand that there is a pattern here. First of all, a strong signal in the center of the cluster is, of course, indicating that it's a real signal. And that is obvious. That was not obvious that on the corners of this matrix, signal is also indicating towards signal and not towards noise. That we didn't expect. And then we noticed that these 2 simple neurons in one layer, so it's a very, very simple brain, already learned causality. It learned that the particle which has produced signal in this pad will travel and produce signal a little bit later in a neighboring pad, but it will not travel faster than light and will not produce signal in a neighboring pad simultaneously with this pad. And also this particle, which is usually it's an accelerator, they're very fast, will not stop in the detector. So it will not start firing the same pad continuously, but it will fire it and fly away. So the neurons learned physics a little bit. It learned that these objects which produce signals, produce it from pad to pad, traveling from pad to pad, with a speed less than light, and don't stop. And so the range of speeds possible in this detector define these corners, the signals in the corners. But what was important for us is to remove the noise. That's why we looked where the weights are negative. So they're negative on such a cross in this presentation. And we concentrated on this cross and just took the input from these cross lines and have pushed it in parallel to two networks. One network analyzed one part of the cross, so the time direction, and the other network analyzed only the spatial direction. And we only combined the outputs without processing further in order not to mix it up again. And this network is inspired by the physics considerations, and it can reach the same accuracy as a complicated ResNet, not with 95,000 parameters, but only with 4,500 parameters. And it works, of course, much faster. And what we also think, it overfits much less probably. And the overfit is a very complicated problem, which we have to really control for, because very sneaky and can hide itself. That's why everything you can do to prevent overfit, you should do. So we suggested this network to the collaboration as the winner because it's fast, it's accurate, it can be run on GPUs or CPUs. ResNet on CPUs is really over the limit long. And so it is possible to use it. What we need to study now, of course, is the efficiency. So this 5% of the signal which we lose, which 5% we lose exactly? We have to test for overfit by making generalization from one energy of the collision in one system to the other and see if the network still works. So that is still work in progress, and I don't know when it will be published, but more importantly, I want to help the experiment that it runs with a good intensity next year. So my summary is that this efficiency is very important to study because we want to not introduce bias in the data. We want to not make the data look as if we have additional particles in the standard model. So this is what also is my passionate topic. I like finding biases and fighting against biases. Also in the company, we're producing products which fight against biases in social sciences. And this is in physics. And I like the fact that the mathematics, which we apply there and here, is the same mathematics, the same language we speak. So let's maybe talk about it. And last but not least, I think as a physicist, one has such a good feeling for data, such a good respect for systematic alternative, for non-linear connections, and for all the things which can go wrong. This is one of the reasons that we have so many examples in the world, much cooler than me, who are physicists, who are now driving AI. So, for example, one of the cool role models is Harmut Neven, who is leading the engineering at Google, who created Google Glass, for example, and the first quantum computer which has supremacy. And he is a student of Professor von der Malsbrook. Giorgio probably remembers him. So thank you very much for your attention. If you have any questions, I see nothing in the chat. You probably want to ask me in person, and you're welcome to do that.
Thank you very much for a good seminar. Apologize for saying I sincerely thought Milk and Sugar was a startup. This was the confusion in the
no problem.
Me. That was it. Questions, perhaps say on chat that you can want to ask a question, because if you raise hands, there's quite a few people. I mean, you've beaten a record today of attendance to the seminar. I won't automatically.
The topic is fun. The topic is fun, definitely.
So anyone has any questions, put on chat and I'll sort of unmute you in line. Anyone? Because if you don't, I certainly have questions. Let me start with
before Giorgio, before you start, I can totally understand that for somebody who for the first time hears about neural nets, this is too many unknowns right now. So if you guys have questions later, write down my name now because people spell it wrong. But if you spell it right, it's impossible not to find me in Google. And then you contact me by Facebook, LinkedIn, email, whatever you like. And then I can answer your questions also later. Or you ask Giorgio.
Yeah,
yeah.
So,
and you can ask now, Giorgio. Yes.
Yeah, I have a question. I mean, you have this. You had this. You talked about this renormalization group and learning as classification. There was a philosopher, not a physicist, called John Searle, who has this famous Chinese room experiment. You heard about it, right?
I think I heard, but remind me. I heard the words.
Basically, there is someone inside the room, and in the room they have lots of tablets, and each one has a Chinese character.
Right. Remember, but you tell.
Yeah, and the point is that independently of the complexity of the rule book, I mean, basically anyone can input questions and the person in the room output questions through a hole in the wall. They have a phone book, which basically is a long list of, if you see this character, output this other character. And this could also, I mean, this list could be even a neural network, in a kind of trained neural network. I mean, the person could get a cookie for each correct answer and get beaten up for each incorrect answer. And in the long run, you know. And the point of this experiment is that independently of how fancy is the algorithm, the person in the center of the room doesn't know Chinese.
So first of all, I've seen, oh, hello, Oleg. I've seen two questions in chat, which I will answer, but first to George.
Yeah, please. Okay, you can answer. Yeah.
What you described is so-called rule-based algorithm. So rule-based means that this person in the room is given a set of rules. If see this character, gives this character. If see this character, gives this character. So this is if then statements. And there is a jump of logic in your formulation. So first we talk about the first part. If he is giving this written down set of rules, that is what is called algorithmic approach. This is what we used until now always, what we learn in university in the computer science. If you take any programming course, what the teacher is following. You have to think what can happen, and you have to give the computer a rule book how to act. So the programmer sits down and has to break his head first in order to define the rules. So this is the standard procedure of programming something. And the difference between this and, for example, any machine learning algorithm, decision trees or deep learning, doesn't matter which one, is that the rules are not anymore defined by the programmer. So the programmer doesn't define the rules in advance, but instead just shows examples. And the algorithm inside the CPU, after the training is finished, for himself defines the rules. Only it's usually so many millions of rules that we don't write them all down and read as a programmer. We just, yeah, okay, you have them, right? Use them. So conceptually, and this is a jump of logic. So you say it doesn't matter if I wrote for him the table in advance or he learned it because I was hitting him with a stick. It does matter. It matters the world. This is the big difference. This is the point. This is the point where it makes the difference. It makes a difference because of the following reason. When you try to define the rules in advance as a programmer or whatever, then you have to attempt to think of every possibility. So like the old computer which won in chess against Kasparov has calculated every possible rule, move and made a rule based on that. So it had inside every possibility calculated. The modern approach says that sometimes in life, it is impossible to think of every possibility. It's just impossible. For example, the game of Go has more possibilities than the number of atoms in the universe. So basically, you cannot build a computer which can calculate every possible outcome of a Go game. And that's why the modern deep learning is so, or whatever machine learning, deep learning is just the fastest. So the machine learning leaves the idea that I will always be right and I will think of every possibility, because it's cool. As a programmer, I have to think of everything, otherwise I'm responsible. This way I give responsibility to the computer. And the computer, okay, it's stupid. It cannot think of everything. It's finite memory, but the clever machine learning procedure makes the computer able to learn the most important information, which again, I as a programmer don't have to decide for him which temperature or pressure is important. He learns by himself what is important from examples. And for that, you need a lot of examples, of course, the data. So basically, the whole philosophy is different. It learns from examples. It will never give 100% accuracy. You will see sometimes 99. Basically, if a person who works for me comes to me and says, I have 99% accuracy, then what I say, yeah, super overfit. Yeah, so I don't trust that. That algorithm I will not trust. If it's so accurate, that just learned the examples by heart. So it's only accurate on this data set. It will not generalize to the new information. So the art of a good machine learning is to learn what is important and what is to be integrated over. So that is done now by a computer, not anymore by a scientist. And the good computer learns what is important, but the bad learns things by heart. So this is the important transition in your logic, is this step between somebody gave him the rules and he learned the rules. As long as he learned the rules from examples and he learned it clever from a lot of examples, he will know the real good rules. And now the question was also, what is the differences in the calculations due to the different CPU speeds? If one talks about only CPUs without GPUs, then of course the scaling is like for normal programming, I think it's n, or n maybe power 1.5 or something. So basically twice faster CPU, twice faster calculation. But if you meant GPUs, that's completely different. For example, for the ResNet, is I compare ResNet and decision tree on CPUs. Decision tree on CPU takes 0.3 seconds. ResNet takes 20.5 seconds. So approximately 100 times, 50 times slower. But if I run them on GPU, then the ResNet is as fast as the decision tree. Why is that? GPU, of course, has very many processors, but not so much memory and not such a high accuracy. So you have to, if you want to run fast of it, you have to parallelize in a clever way. And the modern machine learning libraries, which we use at TensorFlow, PyTorch, they are, I mean, they're based on CUDA, all of them. So basically, let's say CUDA is made in such a clever way that algebraic computations can be parallelized extremely effectively on GPUs. Algebraic computations are the matrix multiplications. Matrix multiplications are used in the graphical unit processing since forever, because this is what makes our videos move. So when you move an object on the screen, what you do is multiply matrices. And that's why multiplying matrices is super fast on GPUs. So let's say the people who love computer games have invested so much money in the development of matrix multiplications that was very lucky for the science. Thank you so much. So the science now uses this fact that we can multiply matrices very, very fast. And instead of writing a complicated nonlinear function in C++ or something, instead we build a neural network, which will also decode a complicated nonlinear function, but it decodes it with help of matrix multiplications, and therefore can run very, very fast on a GPU. So it's a little bit many steps, but I think you understood. That's why GPU is good for matrix multiplications. That's why machine learning is using matrix multiplications. Is it possible to use machine learning for the search of new physics? How to do training in that case? Thank you, very good question. I wanted maybe to talk a few transparency about it, but I had to skip. Now it's my chance. It's called anomaly detection. And that we suggest, for example, to the Bell collaboration. So if we have a detector which is not so noisy, and then what we want to separate is a new particle from known stuff, that's completely different situation. When signal to noise ratio is approximately 50-50, like in all detectors, then we need approaches of classification, which I talked about so much. But if we now talk about completely different situation where we have a huge amount of known physics and potentially very few, like a needle in hay, very few events with an unknown physics, and we want to find these very few events. For that, there is a different method, which is very cool method called anomaly detection. And since I don't want to keep you forever, I just talk very, very fast about it. So basically you can train AI to create stuff, to create new photos, fake news, fake videos, new text, yeah, to write poems. So you train AI to create new events. You throw in all events you have, all. You don't separate new physics, old physics, everything. And AI has to learn to reproduce it, to make a copy of it. So basically to create events, to make a fake news, fake events from the detector. The catch is that when I sit in a Chinese room and have to learn the most important rules, I have to rely on numbers and say, if almost all events look like that, and only 1 in a million looks different, then I ignore this one in a million, because my accuracy will be largest if I produce the most popular stuff. So the events which I produce have to look like an average event. And so I produce a lot of events which look like most of my events. So I can make fake events which will be statistically indistinguishable from my bulk of events. But in this fake stuff, the new physics will be missing. So these anomalies, outliers, the things which happen 1 in a million, will not be learned because they will be lost under the rest. They will be integrated out. That's why the only thing I have to do is now to compare what I measure with these generated events. And if something I measure doesn't look like anything I generated, that's an anomaly. That's in a very simplified way now described. So can you make the machine understand that they commit such errors inevitably, and then it can search for such wrongly classified examples? I think it's approximately what I just described. So yes, you can train a machine to look for examples outside of its learned area. So machine learns an area and you can use it in order to find something which is outside of the area. And if you mean, can you make the machine understand that it makes errors? Computers are stupid. And if you train an algorithm and it tells you for a cat that it's a dog, it wouldn't even say it's a dog and I'm 99% sure, but that's bullshit because it's not sure. But this is what we, in the company, this clever student who is doing very cool stuff. He trains, first of all, for example, many different algorithms, then tests them on a variable data set, very variable data set. And then he knows what are the weak points of each algorithm. And he takes the best one, convolutional neural network, but he knows that in one particular case, this convolutional neural network cannot be trusted. But for example, if you use English words in a German text, theoretically, so you can find cases in which you cannot trust this algorithm. Then you use the alternative algorithm, which you know can be used for this particular cases. So it's a problem which exists, but that the algorithm overestimates is its own confidence. That's a known problem. And this is why you have to always test your algorithm, not just trust. If you download example from internet and run it and get some percents as an output, it's not a confidence. It's just what the algorithm thinks about itself. The chess champion of 40-60s, Botvinnik, was also a leader of developing program for not using the full moves tree analysis. May it be it was a sort of ML. I think that Botvinnik was, I mean, I don't know this work, unfortunately, I have to read about it, but from your description, I would say, because he developed this program, and because also in the 40s, 60s, the computers were not fast enough to do the usual deep learning, the computer was not finding the rules himself, but the Botvinnik was finding the rules. And it's clever that he didn't let computer calculate everything, because Botvinnik had intuition. And his intuition was telling him, for example, that what this Peshka, so the soldier, is moving in the far right corner from my queen. Sorry, how's it called?
Pound, I guess.
Yeah.
So, pound. Yeah.
Pound. Okay.
Yeah.
So what this thing is doing far away from my king can be integrated out, but Botvinnik knew it. That's why he defined for each type of position which are important moves, which important moves you have to consider in your tree, and which moves you can forget and they're not important. Don't even try them because they're so obviously wrong. But this is exactly the let's say old AI approach, because the person had to put his intuition inside. And if this person is the best genius chess player in the world as Botvinnik, that's fine with me. The problem was, for example, that in the new deep learning approach, the idea, the scientific innovation was that Google tried to let the computer develop intuition and not to learn the intuition. The championship against Go, let me remember, I don't know, I think 2013, AlphaGo tried to play against the champions and it won over all vice-champions, but it still couldn't win over the best champion in Go. Because it really did this approach, it learned from examples of old games and it learned from playing with these vice-champions. So it could absorb the intuition from these vice-champions, but it didn't have the intuition of the genius. And then 1 year later, AlphaGo beat them all, including the champion 8 against 0.5 or something. How it happened? Because of the new idea in the AlphaGo, in Google AlphaGo, that two deep minds had to fight with each other millions and millions and millions times without even talking to a person. So they have developed their own intuition, which was sometimes different from our human intuition. And in one of these 8 victories over the champions, over the main champion, in one of these 8 parties, AlphaGo made a move which no human would make. This is very famous because somewhere it has, in the course of the party, it has put a white stone far away from the strategical area, very far away. No human would do that. That's stupid. You lose time. And if you lose time, you can lose the whole game. And it was losing time developing a position so far from the strategical that it looked stupid. Then, approximately 100 moves later, that's what saved the victory. That white stone, which was put 100 moves ago, really allowed AlphaGo to win. And that was an intuition which was not part of any human intuition, which was developed by learning, by just simple playing with each other between computers. So that's pretty spooky. What are the methods you are currently using to avoid overfitting? Yeah, see you, Graziano. So for the overfitting, yeah, overfitting is a big problem. And I am very strict with overfitting. That's why I'm successful. So there are some well-known, okay, how it's called in English, wait a second, rules of thumb, let's say, you can follow, but there is no guarantee. There is no warranty against overfitting. So first of all, you will never be 100% sure that you are not overfitting, and you will never be 100% sure how to avoid it. There are situations where you just don't have enough data. For example, in the University of Gießen radiology, they have data of 200 patients. And there, I just told them from the beginning, forget it. Whatever you do will look good, will seem to have good accuracy, but it will not be useful in practice because it will be an overfit. So just academical investigations, very good, practically not applicable. When in the University of Frankfurt, unfortunately, because of the COVID, they collected many thousands of patient data, also from many thousand patients, each patient many data. That's a completely different story. There you can really already start working. So you have to have enough data. Then the data have to be of good quality. Example, from the field of the company I'm working, we are in the company developing solutions for the recruiting, for hiring people. And what we don't do is that what Amazon tried. They learned on the old data how to tell from a resume if this candidate is potentially fitting, potentially good programmer, and then filtered and only have shown to the human recruiters maybe 1/10 or 1/100 of the resumes. I mean, Amazon gets a lot of resumes, and then out of these chosen, there was a decision made, and I think they have chosen very few. So basically, they really reduced very strongly. So a big part of the decision was by the computer. Then 2 years long, they were hiring only men until somebody noticed that something is fishy. Because algorithm is not stupid and has noticed that the parameter gender is very good feature to decide if this person will be hired or not. In other companies, a parameter, American company, name sounding as Latino was a good parameter to throw away this resume also. So that we shouldn't do. That means we trained on shit, we got shit. Yeah.
Just let me, I'm sorry, I mean, you're saying something, and this was something I wanted to ask, which directly is relevant. So I just want to add this. There was a book written a couple of years ago called Weapons of Mass Destruction, which is exactly what you're saying now, that using artificial intelligence systems in things like recruiting, giving loans, and things like this, a lot of research that says that it reproduces 100% the prejudices the society had in advance. I just wanted to say this, and sorry for commenting this.
That's a very good comment. Exactly. This is something we have to keep in mind. So the bias which is in the data will also be learned and will be part of the decision. And this is very important. So for example, in physics also, so the bias, the systematical error, and so on, it's very important. We know that in physics, it's a big problem when you have a biased data, then you get a biased theory in the end. And the same as in every other science, only the problem is that in social science, a lot of people don't even know math. And so for them, it's difficult to fight against it. But we are keeping it in mind. And for example, as maybe I even mentioned here in my Outlook, There are approach by Gregor Kasieczka how to reduce bias in the physics data, which he also applies in collaboration to reduce bias in their loan decisions. So just removing the name and gender from a resume in your data still doesn't remove the bias. It's not so simple because there is a lot of indirect indicators which are still there. So it's much more complicated than that, but there is a whole scientific direction to do this. And since neural networks somewhat mimics the layered structure of the brain, yes, they do. How far are we to using such artificial networks to understand the brain itself? Super questions. Just a moment. I work with EEG data and I wonder if we could construct a neural network that has nodes in specific regions. These nodes interconnected just like the brain and also possibly mimicking the architecture of the brain. Especially, do you think that's possible? First of all, I think it's definitely worth trying because it's a wonderful topic and it's great to do something so interesting if you want to collaborate. I think it's also very complicated because in FIAS, a whole big part of FIAS is doing it. It's simulating brains. For example, Professor von der Weisburg also. And what I understand from their results is that just a forward neural network, what I was describing, all these artificial networks, they have in common that they are so-called forward neural networks because the computer inside is actually executing a program from beginning to the end. However complicated the program is, it cannot turn the time back. While in the brain, there are sometimes connections kind of backwards in time, and this is memory. In brain, we have memory, and that memory is very difficult to model in an artificial brain. And so this is just one of possible directions, and not the only one, but the one which is followed, for example, by Professor von der Weisburg, is that there are circular networks, so that the signal is sent from neuron to neuron, neuron to neuron, and then comes back to the original neuron and goes again. And you understand it's an infinite loop. That's why no computer can simulate that. But this infinite loop in physics terms is not so crazy because it's just a closed circle. And closed circles at the normal electronics, it's a resonator. So every physicist knows what I mean. Yeah. So it's every electrical circuit which is closed is not crazy, it's just a resonator. That's why the theory of von der Weisburg is that in the brain, we don't have neuron connections from A to B. Instead, we have neurons in circles inside the brain. I don't mean with the spinal cord, I mean the head. And so these resonators connect with each other. In this way, one can maybe model memory. It's very exciting topic. Great. We are so much over time. Giorgio, you have to kick me out.
No, I mean, as I said, the boundary is fluid. If there are any more questions, if there are many more questions, and if you don't have to go anywhere, I'm not kicking anybody out. Maybe they'll kick me out because I am on the Zoom account of the head of the department.
Awesome. So you will be kicked out.
Yeah.
Thank you.
So any more questions? At the moment, I can't really think of any either, but this was really good. And I actually have the one thing you actually taught me is to encourage people to ask questions over chat because it was the first seminar by number of participants and also by far by the amount of quality of the discussion after the seminar, which is
my pleasure.
Encouraging.
My pleasure. So, if you have a recording, in any case, I would be happy to have it, and I will let you know as soon as Marek answers I already asked him on email, and well, let me see if he answered already. I'll stop sharing.
I'm stopping to record now. Do you want to stop cloud record?